So, you started? Good. This is going to be like more or less an extension of the previous talk that I gave this summer in Brussels. Unfortunately, for like tragic reasons, it wasn't saved. The camera died last time, but more or less, like the message was that I will cover some parts of the previous message in this presentation as well. So here I want to present the next frontier in software supply chain security, which we call autonomous build network. It's a initiative to try to create a currently non-existing link between source code and binary, and like apply the same principles that we use for like doing let's say software version control to producing and building packages. So like in also we'll cover some details on image generation in the second part. So this is how software supply chain security, software distribution looks today. We have below Merkle tree on the left side, and then someone builds a package, and then someone signed the package, and then someone received the package. There is no real link between or any credible guarantee that the thing you are running is actually the source code that it's supposed to correspond to. People tend to like spend like a lot of time like trying to create and tools for checking the logic of applications and like try to formally verify applications. And then what happens next is they throw the source code into a huge tower of transformations. No one actually understands how it works, and then it produces big binary that then supposed to be shipped and run. So yeah, and if you want to produce binaries, have on your own, you don't have real like practical tools to do that. Currently, like anything you want to do on computers, like in general, is like you have to always ask for permission in some way or the other. Like you either relying on distribution, like community that provides the distribution for your operating system, or you're relying on like your network infrastructure. But there's no way for middle-sized and small teams to have their infrastructure be dependable and manageable in a way that like it's actually legible to them. Yeah, so there's like a list of problems. It's a network of single point of failures, not reproducible. There's little conversation about how to bootstrap binaries, and yeah, and as I said, no practical way to run your own infrastructure. So what is autonomous build network? Autonomous build network is basically like adding another Merkle tree, which is concerned with the inputs to outputs pairs. So it's an attestation network, meaning that this is just, it's not a blockchain, it's a Merkle tree that allows you to have credible, like not a proof, but like some credibility over the link between binary and the source code. How it's done is that you have a set of network validators or like builders who build the packages, given you have the way to reproducibly like have the reproducible builds and a zero binary like zero binary bootstrap seed. You can have the DAG of all the software artifacts, and the Merkle tree is just a collection of input to output pairs. So what goes into the build and what goes out of the build. And the good thing about that is also you can add the content address network, content address storage, which is, or like you can basically swap any transport backend you want. Yeah. This third line, OS image is first class artifact, is I'm going to explain actually in the next section of the talk. Yeah, this was another question. There was a question in the previous talk that I gave in Brussels. This thing, this is what people usually ask. Like, is it like for reproducible builds for T's or T's for reproducible builds? The fact is, it's both. So you need to, you don't need T's for reproducible builds, and you don't need reproducible builds. But you need reproducible builds for T's. But at the same time, TEs can enhance the reproducible builds. And in our case, this is just another high credibility attestation. The fact that you have like some sort of like verifiable computation, but it's like not verifiable. It's like attested by the like Intel. Yeah. Now, how do single builders, like the agents of the network, actually carry out the process of creating packages, and what does it mean to have a first class, like have a operating system image as a first class? It was touched upon in previous presentation, so we're using very similar tooling, but it's a project that has been descendant of Nix OS, which is called Geeks. And this is the thing you can build on your own. You can build your own kernel, you can build your bootloader, initial RAM disk, packages, and the thing is, like, what does it mean to have a file system as a file? You can mount file in as a file system. You can mount file as a disk, and then you can create a partition table. You can put stuff into it. We have the virtualization tools to do that, and I'm not understanding why we're still continuing this trend of mutating systems like with live connection. This is what people usually do when they administer and orchestrate systems. You like have a SSH connection, you connect to the thing, you run some commands, and you assume the network connectivity of the machine, whereas here you don't really assume anything. This is just a file. So kernel is a file. Yeah, you go of files. Yeah, and this has some nice side effects. So when you treat this like your build process like that, you can put like cloud init into your initial RAM disk. So the first thing gonna happen when you boot your cloud init image is that it will reconfigure your system based on the metadata it's given on like link local address or on like plugged file system. Or you can place things that you would place afterwards through a live connection into the image from get-go. Because you can reproducibly create the guest image in our context for the TE. You can just put your SH keys, you can configure all the services you want without like assuming that you will have to mutate the system afterwards. Yeah, I mean, so a couple of months, I've been looking into providing like TDX support. Some of these things, most of the things that have been done, some of them are like non-existent and require some further development. But basically, like this is just declarations in like in a Geeks configuration language, and which is a fully it's a program like Turing full-fledged programming language that you can use to only configure, create package definitions, but also like have define arbitrary things during the boot and build process. And as a result, given all that, you can just have a CI that produces all those artifacts. We can produce custom host image, guest image, install media, and a cloud image. Currently, cloud image is the thing to come next, because like this requires a cloud init replacement, but the three other things I've already implemented. Yeah, I mean, oops, it's too big. So this is like how the operating system declaration looks like. It's really it. The declarative nature of configuration actually tells you to just tell what's going to be in the image. And in our case, the thing I'm working on right now is this part, a TDX service wrapper, which is a thing that's gonna wrap any service you want and place it into a guest image in declaration, which is like a macro. They will produce a guest image, and then all these things are done behind the scenes. So the TDX wrapper is just a service that's gonna run the virtual machine itself. Okay, good.